So most of this is notes, so just relax anyway. Electrolytic cells. Today we're going to talk about electrolytic cells. Here we go. Electrolytic cell uses electricity to force a non-spontaneous redox reaction to take place. So in today's lesson here, we're going to talk about obviously kind of the opposite of a voltaic cell, guys. Opposite of voltaic cell. We're going to talk about electrolytic cell. Electrolytic cell, of course, means that we have to use electricity or some type of energy source to basically force that reaction to take place. Voltaic cells, of course, are spontaneous. So when you're using your cell phone, right? You got it. Your cell phone's right here. Check this out. Ooh, nice. You know, you're using it. Beep. Right? I'm using it. Voltaic cell. But what happens to the voltaic cell eventually? It dies, right? So we need to replenish it. We need to recharge it. So to recharge it, we need to plug it in. You got 5 messages. Actually, that's a lie. You got none. I erased them. So in order to recharge it, okay, you need to plug it in, right? That is your electricity. That is how you're going to force that reaction. Right now, it's running as a spontaneous, right? Spontaneous reaction. And we're going to force it into a non-spontaneous reaction. So we're going to force the electrons the other way, basically, to recharge that battery. Now, it doesn't have to be just recharging a battery. So let's not just say, oh, we've got to use, it's always got to be the opposite, et cetera, et cetera. No, not necessarily, okay? But that's a good example of what would take place there, okay? In some cases, electrolytic cell can be used to set up the reverse reaction of a voltaic cell. So it doesn't have to be exactly the reverse reaction, but we could do that, okay, with a voltaic cell. This can recharge the battery, okay? If you remember the Danielle cell, and there's actually going to be a picture here coming up for you guys, so even if you forget it. Danielle cell, of course, was a special type of cell that we talked about. It used copper and zinc, remember? Zinc lost electrons, copper gained the electrons, right? Zinc was the anode, copper was the cathode, and you can go all the way back and look, or you don't have to. Electrons spontaneously flow from the zinc anode to the copper anode, because remember, copper 2+ is the SOA, zinc is the SRA, right? And we had this spontaneous reaction, yes? As always, spontaneous, okay? There's what it looked like if you forget, okay? We got a nice little diagram here for you. And of course, don't forget, people, that electrons flow to the cathode, and they flow from the anode, okay? So, in this case, of course, copper, cathode, electrons are being reduced at the cathode, right? Or sorry, copper is being reduced at the cathode, gains electrons at the cathode, anode is losing electrons, and this is what we kind of saw, right? And, you know, other observations you'd see here, by the way, guys, is that the zinc, of course, this solid electrode would get eaten up, right? It would dissolve, because it'd be changing into zinc 2+ ions. And the copper 2+, this would build up over time, right? Eventually, if you left this long enough, this reaction is going to slow down, possibly even quit, okay? Things that could happen, you know, the zinc electrode could get used up, okay? The copper might become very, very coated too much, whatever. You might be running out of ions here, so you might be running out of zinc, of course, to make zinc 2+, but you might be running out of copper to make more copper, okay? So those things could happen there. If we wanted to reverse it, in other words, if we wanted to kind of recharge it so that I could use this again, you know, for example, we could, you know, we could run something off of this, okay? We'd have to look up the volts and see how much, of course, and if, you know, it's really that big of a difference. But we could run something off of this, but at some point in time, it's going to decrease, okay? So what we might want to do is recharge it up, kind of thing. So we might want to reverse the flow of electrons. In order to do that, we need to hook up a power supply, okay? To recharge the cell, a power supply is added which reverses the flow of electrons. And it would look something like this here. And you'll notice I still have the copper and the zinc in the same spots here, okay? Couple things to note, okay? The reverse is happening now, right? So if you look here, the copper is losing electrons now, okay, to become copper 2+. So it is being oxidized here. Technically now this becomes the anode, okay? And the cathode still always gains the electrons, so that never changes, okay? And we're going to show you a little chart to compare these things eventually. Let's not jump ahead, though. But the cathode is still gaining electrons. Reduction always happens at the cathode. Here's the cathode. Reduction happens at the cathode. Oxidation always happens at the anode. What's changed here is which elements are being oxidized and which ones are being reduced. Okay? You'll notice, look at the salt bridge for a quick second. Cations flow towards the cathode still. Anions still flow towards the anode. So in that salt bridge, where they were before, if you look back here, right? Here's the cations here, here's the anions here. Actually what happens is they would switch. So the cations would flow back over to here, and the anions float there, the cations would float there, so they're actually going to switch. The cations always go to the cathode. Reduction always takes place at the cathode. That never changes no matter what cell you're talking about, voltaic or electrolytics. Okay? So, cations towards the cathode, anions towards the anode. Reduction always happens at the cathode no matter what. Okay? In this case, of course, you know, remember, copper is losing electrons. Those electrons come up here. They are pulled by the power supply. I'll talk about that in a second. They come over here, and the zinc is going to get replated on there, basically, or it's going to build up with another zinc mass there. Okay? And then if we unplug the power supply, it would switch back to the other one. It would be making zinc ions again, and the copper would be adding itself back on again. Okay? Copper 2+. The power supply is the key here. We have to be able to pull electrons from basically the copper, okay? So this power supply, you'll notice, has a positive here. It's pulling the negative electrons towards it, okay? So the power supply pulls the electrons towards it, and then on the other end of the power supply, it is a negative. It's pushing the electrons away from it, okay? So it pulls electrons from the anode in this case, and it forces them towards the cathode. Okay? And we'll talk a little bit more about that on the next few slides here. All right? What are some differences between voltaic and electrolytic? And we'll talk about that. But one of the biggest differences, when you look at a diagram, you are going to see a power supply. As soon as you see a power supply in this bridge here, basically, you will know it's electrolytic. Okay? That is your key to know that that's an electrolytic cell. All right? So, when you see that, like I said, you'll know it's electrolytic. It's a non-spontaneous reaction, in other words. The power supply pulls electrons from the copper and pushes them onto the zinc. Okay? This forces the oxidation of copper and the reduction of zinc 2+. We talked about that already as well. The power supply forces copper to act as the anode and the zinc to act as the cathode. And we see that from the diagram there, of course, as well. So in other words, zinc being reduced at the cathode, zinc. What is the difference between, and we're going to use this Danielle half cell here if we want to compare the two of them directly to each other. What's the difference between the voltaic and the electrolytic? Well, first of all, obviously the first thing is the voltaic one is spontaneous, the electrolytic is the not spontaneous one. Okay? Think about it. Voltaic cells convert chemical energy, right? So the process of electrons freely moving from spontaneous reactions, so SOA to SRA kind of thing, or SRA to SOA, I guess. But spontaneous reaction converts that transfer of electrons, that's the chemical energy, to electrical energy. So it's converting, you know, chemical energy right now into electrical energy. In other words, I'm using it right now. Okay? The opposite is electrolytic cells, you plug it in. So you're using electricity, basically, to convert it to chemical, potential chemical, which then when you unplug it, your battery's charged up. Now I can do chemical, okay, again. And then I plug it back in, and I use electricity to convert it back to chemical again. Okay, and that's really what you're doing when you plug in battery chargers and things like that. Oxidation, of course, for the voltaic cell. Now this is specific for, like I said, the Danielle half cell. In the voltaic one, zinc was being oxidized. In the electrolytic one, it's copper that's being oxidized. Okay? Obviously opposites. They don't always have to be like this. Of course, we're giving you a specific example here, so you have to be aware of that. Yep. Yeah. Yeah. They switch places again. So they basically float to the other side. The net cell reaction will be a little different because, remember, look, if you're adding these up, zinc solid and copper 2 plus gives you zinc 2 plus and copper. But remember, with the electrolytic cell, we're doing kind of the opposite. So if you look here, it's copper and zinc 2 plus gives you copper 2 plus and zinc. So it's slightly different. Okay. Remember, the cathode and the anode have technically, they switched chemicals there. And you can see that right here, actually, because in this case here, if you take the cathode minus the anode, a spontaneous reaction, it's a positive 1.10 volts. Well, if you flip that around, what happens if you take the zinc, which is now the cathode, remember, and the anode is copper, it's a negative 1.10 volts. So you get actually the opposite. Okay? So, spontaneous reactions, and we'll talk about this. Spontaneous reactions are positive. Okay? Non-spontaneous are negative. Absolutely. All the time. So, electrolytic cells will always have a net of a negative volts. Spontaneous will always have a net cell potential of positive. Always, always. Okay? A negative value means that the reaction is non-spontaneous. This represents the minimum energy that the power supply must provide to drive the reaction. So, we have to supply, you know, for example, back to this one here. This is a minus 1.10 volts. If I didn't apply, you know, if I want to recharge this battery basically, or this Danielle half cell, if I want to replenish that and basically get it back, I need to submit at least 1.10 volts, at least that much, to basically force the electrons in the other way. Otherwise, they will not go. They will keep running in a spontaneous reaction. If I want to do the non-spontaneous, it's going to require, okay, it's going to require at least 1.10 volts in order to basically force the electrons the other way. Okay? Probably the more you can put in there, the better off it's going to be. The faster it's going to go, right? In most cases. That's why, you know, when you guys have, who's got iPads and iPhones? Yeah? You guys got the big charger and the little charger, right? Yeah? And the big charger goes faster because the iPad's tougher to charge, right? Well, it supplies more voltage, watts, whatever. So when you plug in the, you know, when you plug in the little one and you plug your iPhone into it, you know, it charges, however fast. But if you ever take the big one and use the big one to plug it into the iPhone, it goes a lot faster, charges a lot quicker, right? Because you're overcoming that barrier by much more, okay? So, and you can do that or not do that. It's up to you. Just so you know. Some people say it wrecks stuff, but I do it because it's faster. Yeah. Yeah, because basically what's happening there is when you go to recharge it, and this happens with every like with most batteries, is, you know, you're not probably going to get back to 100% efficiency all the time. In other words, some of that stuff might get lost. You know, sometimes it bubbles out, or a water solution bubbles out and things like that. So, you know, they only last for a period of time, right? Even doing that, you're going to have some kind of loss. So it's not perfect, right? With that. So, yeah, that just happens over a period of time. Okay, let's see. Most electrolytic reactions require a minimum amount of electrical energy that is somewhat larger than the indicated E net value. The additional amount of energy is known as the cell's overvoltage. Okay, so the additional amount of the energy is known as the cell's overvoltage. Okay, we're going to give you an example here. So if you look at, for example, potassium iodide electrolytic cell, you might say, how am I going to know if this is a voltaic one or am I supposed to be using an electrolytic one? Well, first of all, you're going to do the same steps you did before. You're going to write down all the stuff that you have. Secondly, it's probably a little bit more obvious than that. It might show you a diagram. It might tell you that you have to pass electricity through it. So they'll tell you key words that you should be looking for. if I have to put electricity into this cell, well, that is an electrolytic cell, of course. If they might say it's an electrolytic cell, they might say it's a voltaic cell. So there's going to be key words that you're going to have to pay attention to and really focus in on those so to know what you're actually trying to do here. Okay? Now you might say, well, how am I going to know? What's the difference? Like, let's take a look at this one. It says electrolytic cell, first of all. And secondly, like I said, they're going to give you a little key word there, but there's also only certain options you're going to have. When you do a potassium iodide electrolytic cell, okay, those are really the only things that you have present in this example here, okay? So once again, how are you going to structure this? How are you going to do this question? And the answer is, you're going to do it like you did every other one. You're going to find the SOA, so you're going to work in the top left. You might say, but it's electrolytic. Doesn't everything have to be backwards? And the answer is no. Which one is the most likely to gain electrons? Which one's the most likely to lose electrons? Same thing, okay? So no matter what, you still do the same thing. You're going to start here, and you're going to start working your way down. What's the most likely thing to gain electrons? What's the SOA? And I think in this one, it must be water, right? So you guys have this example already. It's water is the most likely to gain electrons. That's the first one I come across as I start working my way down here, okay? So that's the first thing I come across. Start in the bottom right and start working up. What's the first thing you're going to come across there? And the first thing it comes across is this up here. This is your SRA here, okay? What you'll notice, of course, is the SOA is lower than the SRA, right? Now we get this kind of thing here, right, in your data booklet. So pretty quickly, I hope you realize that that's not spontaneous. It is electrolytic. And that's kind of what you're looking for, obviously, because it says it's electrolytic. So it should be non-spontaneous, I'd hope. Okay? So then you'd write out the two parts to this, which we have on the next sheet here, and I probably should have made you guys do this. But we'd write out what's happening at the cathode. Cathode reduction always happens at the cathode. So this is reduction because it's gaining electrons right here. So the cathode, always reduction, of course. We write that one out. What's being oxidized? Same thing as before. That always happens at the anode, which mine got cut off here, but you guys have that one there. It's what, the 2, is it 2I minus here? And that gives me what, I2 solid? I don't know. Is that what this one is? Yep. I2 solid and 2 electrons, right? So, and then of course you still have your net cell reaction, okay? And when you add all that stuff up as your net cell reaction or your redox reaction, and then you could say, what's my net in this case? What's my net cell potential? Well, you would say, of course, the cathode minus the anode. The cathode happens to be, in this case, though, where did it go here? Where's water? Water. Negative 0.83 volts minus, and it turns out that it's the iodide one, yes, 0.54, right? So subtracting those two, of course, you're going to end up with your negative, what is it, 1.37? Does that sound right? Negative 1.37. Okay. So once again, because it's non-spontaneous, it's negative. All right? So that would be your cathode minus anode there. What would you see, of course? Guys, listen. What do you see at the cathode, for example? We could still look at observations and things like that. What would you see at the cathode? Well, you'd see water changing into water gas, or sorry, hydrogen gas, I should say. So you'd see some bubbles form, and once again, you'd see the pH probably go up in this case because it's going from something waterish to more basic. Okay. At the anode, mine kind of got cut off here, but this I2 here, you'd see this mass. You would start to see iodine crystals starting to be formed. Okay, reddish brown color it says in your notes. Once again, you won't have to know anything about the iodide because it's not in your data booklet, so you're probably fine with that. But you would see something like that happen there. Okay? Yeah, so there's that. Once again, yeah, there's the cell potential there for you, net cell potential. And once again, a minimum of 1.3 volts must be input before the reaction would take place. Because, like I said, it's basically that's the net cell. Okay, now this is there's always exceptions to the rule, of course, and there is one exception with electrolytic cells. When you're passing electricity into this cell here to force it to go the opposite way, the chloride anomaly happens when you have water and chloride together. So if you look in your data booklets, guys, and you need to get those out, and if you find water and chloride, and it says here, of course, now keeping in mind, of course, as the only possible RAs. So if you're looking at the SRA and you're trying to find water or chloride as your SRA, you, of course, would start in the bottom here and start working your way up, right? Because that's where the SRAs are. So you're going to start working your way up. You're going to go up and up and up and up and up. And it's quite high up there. So, you know, if you had other stuff here, this doesn't apply. If you had some bromide or, you know, I don't know where bromide is here, but if you had something, you know, down here, you don't need to worry about it. But when these are the only two SRAs, or sorry, I guess because they can't both be SRAs, but if these are the only two RAs that you have, the only two possible ones, well then something happens here, okay? Normally we'd start in the bottom and start working our way up, and the first thing you'd see is actually water. Comes before chloride, okay? Water, by the way, is where I'm looking here, is at about, right there, 0.23. 1.36. So most of the time when you're doing this, you'd say, oh, it's water. Okay, water is my SRA. That's not the case. Okay, so that's what we would normally pick, but it's not the case. The chloride anomaly, it only happens with water and chloride. So what happens is, it's actually the oxidation of water is so large that chloride ions are actually more easily oxidized. Okay, remember, if it's a reducing agent, it's being oxidized. Chloride is actually more easily oxidized than the water is. And we can go back to activation energy kind of for this, and that's what this is. So if you remember, activation energy kind of looked like, that's probably not a great diagram there, but okay, so something like that there, for example, for one of them, and the other one would look something like, I don't know if it started exactly the same spot, but let's say it does, might be so high, and yes, it might be difference down there, but to get that reaction to actually take place, that activation energy is very, very high. And we don't need to know anything more about that other than the fact is, when you got water and chloride, you mostly likely would probably pick the water, but it's not. It's the chloride in this case. Okay? And it talks a little bit about that here, basically. As electricity is supplied to the aqueous solution, the chloride will be oxidized to chlorine gas instead of the water being oxidized into oxygen and H+. Okay? Yeah. Okay? So that's one of the things you just kind of got to remember about that chloride anomaly. Okay? So let's get you guys to write out this one here. I'll give you a few seconds here. You can pick out some stuff here for this reaction here. Most likely reaction to take place when electricity is passed into a solution of cobalt-2 chloride. Okay? Key words here, like once again, what was I talking about? I said look for key words, right? How do you know what kind of reaction this is, etc., etc.? When electricity is passed into. Okay? So when you think about this one, you're thinking about electricity. Hey, that's got to be an electrolytic cell, okay? Because I'm putting electricity into this. All right? Okay, so this is kind of your list you want to start with here. Cobalt-2 chloride, water, okay? At the cathode, of course, you'll see cobalt-2 plus and 2 electrons. Gives me cobalt solid. At the anode, okay, you got the, well, water. Or, of course, and you go back up to here, of course, this will be your SOA here. And you got a choice between these two here. Water is the first one you see, but in this case, remember, water, tougher to do, so we're going to go with this one here, the chloride one. Okay? So, chloride, Cl minus, and, actually, sorry, Cl minus, that'd be 2 there. And then Cl2 gas, and 2 electrons should be. And then you could just add those 2 up, of course. So net cell reaction here. what is it, cobalt 2 plus and 2 chlorides gives me cobalt and chlorine. That'll be a gas actually there, and solid. Okay, and that should be balanced, I think. And then, of course, what's your net cell here? Potential, in case you want to do that. Well, C minus A, of course. The cathode here in this case, of course, is the cobalt, so that's a negative 0.28, cathode minus the anode, right? And the anode is 1.36. Okay. Adding those two up there, negative 1.64 volts. Okay. Now, some people always say, okay, well, so that's the minimum you need, of course, to make this reaction and take place. Okay, you'd have to put in at least 1.64 volts to make this reaction take place. What about some of the other stuff that's that we could talk about here? So some people say, well, before we did cobalt 2 plus, we did cobalt solid, we did chlorine gas, et cetera, but remember, they're going to tell you what kind of reaction this is. Some people say, well, if I got chlorine here, I see chloride up there at the top, and there's also something like, I don't even really want to write it down, but there's Cl2 gas, right? Is that going to be part of this system? Sure it is. It's going to be produced, obviously, but some people would say, well, why don't we start with chlorine gas then, Cl2, because that's the opposite of chloride. Why don't we start with cobalt solid? But the question is that spontaneous or non-spontaneous? Right? And you got to look that up, and you got to see, you got to kind of judge for yourself, could I use Cl2? Could I gain 2 electrons? Sure. But then you're going to get down to possibly water or cobalt. That's farther down. And of course, you got to use the that's going to be oxidized. But the problem with that reaction is that becomes a spontaneous reaction. You don't need electricity for that one. So it can't be that, it's got to be this. And usually with these types of electrolytic reactions, they're going to tell you exactly what's in there. So cobalt 2 ions, chloride ions are probably the ones that are a safe bet for you. Okay? They're not going to be talking about the cobalt solid and the Cl2 gas. And you're not going to have to look on both sides of the reaction as much probably for those types of reactions, because like I said, we're talking about changing this and we're passing electricity into this. So we want to focus probably on these here. And I don't know if you kind of call what I'm saying, but before we said cobalt 2 plus, oh, would there be any cobalt solid? Probably, yeah. Probably we could write that down if you wanted to. I don't want to here, but you could, cobalt solid. Is there Cl minus? Yes. Is there Cl2 gas? Yes, there is. Okay? But once again, if it's an electrolytic cell, then you have to be careful what you're trying to pick there. If you pick the Cl2 gas, well, that pretty much determines that that's going to be a voltaic cell, and we don't need to do that. Okay, we're looking for the electrolytic one here. Okay, so that kind of gives you an idea for that there. Okay, and we'll give you some time to work on some questions here. And there is another diagram I want to show you, but I didn't get around to it first class, so we'll probably do it first tomorrow, which means we'll have a lot of stuff to do tomorrow. Tomorrow we're going to do some application of electrolytic cells, so we're going to do a little bit more of that. And then Wednesday, Thursday, we're going to do Faraday's Law, and then we're done. And Friday we'll probably start some organic, do a little bit of review. We'll start some organic. And then Monday is probably more organic, and then Tuesday is your test. Okay? Yes? It is a non-spontaneous reaction, yeah. This one right here? Sure. Non-spontaneous, yeah. And you would need to, like I said, apply at least 1.64 volts to get that reaction to take place. Okay? So, okay.